again welcome in the next class. Now today's topic is Faraday's laws of electromagnetic induction. So here there are two laws. First is known as qualitative law. First law is known as a qualitative. So qualitative law states that whenever the magnetic flux linked with the closed circuit changes and EMF is induced in the closed circuit, which lasts so long as the change in magnetic flux take place. That means there will be induction of EMF when there will be change in magnetic flux. If there is no change in the magnetic flux, there will be no induction of magnetic, or you may say EMF or the current. Second is quantitative law. Quantitative law. Now it is very important. The magnitude of induced EMF in the closed circuit is equal to the rate of change of magnetic flux linked with the closed circuit. Here we will see that phi 1 is the magnetic flux passing through a closed surface at time t1, and phi 2 is the magnetic flux at time t2. So according to Faraday's law, EMF induced, this is directly proportional to the rate of change of magnetic flux, that is phi 2 minus phi 1 t2 minus t1. So this is the rate of change of magnetic flux. Here we will see this is equals to a proportional constant phi 2 minus phi 1 by t2 minus t1. In SI unit, value of K, this is equals to 1. So we can say EMF induced is equals to phi 2 minus phi 1 by t2 minus t1. This is here. This phi 2 minus phi 1, this can be written as d phi b by t2 minus t1, that can be written as dt. Change in time change in magnetic flux. This is here. If suppose the coil has n number of turns, then EMF, this will be equals to n times of this EMF. So n d phi b by dt, where this n is the number of turns in the coil. Suppose that coil, that circuit has its resistance R, then current I, that will be equals to, no doubt, that's EMF induced, magnitude of the EMF by R according to Ohm's law. So this will be equals to d phi b by R dt. Here. Now we will see, this is the value of the current. Now we are going to say here now different methods of producing induced current. Definitely EMF can be produced by changing the area. Formula you know very well, d by dt, this equals to dA cos theta, and this is equals to, this equals to EMF, this equals to. So here we can change the B, we can change area, and we can change theta. So on these three factors the EMF induced depends. Now Lenz's law. Faraday's law does not tell us regarding the direction of the induced EMF or induced current. Now it is modification of Faraday's law, Lenz's law. This gives us the polarity, means direction of the induced EMF or induced current in a closed circuit or a coil. Here the polarity of induced EMF in a closed circuit or a coil is such that it opposes that cause, which opposes that cause. So according to this Lenz's law, EMF induced is equals to minus d phi b by dt. This negative sign shows that induced EMF opposes the rate of change of magnetic flux in the closed circuit. Second thing, suppose there is a loop and a magnet is dropped or moved in this direction. A magnet is moved in this direction. Here is the north pole, here is the south pole. Then definitely we know here that magnetic field lines that come out from the north pole. and here you will find that current is or induced current is developed in that coil. Here in this coil it moves in this direction, then we can say in this direction, and here now the current moves in this direction in different magnetic field lines. Similarly, when it is magnet is moved in this direction, here is north pole, south pole, so in this case magnetic field lines increases and here now decreases. So we will see magnetic field lines here, the direction of the induced EMF, that will be here in opposite direction, and here now it is in this direction. So this is Lenz's law. Now Faraday's right hand rule, you know about the Faraday's right hand rule. This is, so if we stress forefinger, middle finger and thumb mutually perpendicular to each other, and these points means forefinger points towards the magnetic field, then this thumb shows the motion in the conductor, then this will show the direction of induced EMF. So I think it is clear. One thing I am going to say, that one situation. Suppose a copper ring is held horizontally like this, here, and a bar magnet of mass m is dropped. Bar magnet is dropped through the ring, this side, or you may say along its length, along the axis of the ring, like that. So compare the acceleration of the magnet. Suppose acceleration of the magnet is alpha, or you may say A, better to say A of the magnet. That of the acceleration due to gravity. Acceleration of due to gravity is G. So simply we are going to find out relation between A and G. Again try to listen my situation. There is a horizontal copper ring, and through a bar magnet is vertically dropped, which mass is m, along the axis of the ring. So we are going to say what will be the acceleration of the magnet. Relation between this acceleration of the magnet, we are going to find out the relation between A and G. Definitely we will see when the magnet comes near the ring, an induced current is developed in the ring which opposes the cause. This ring repels the magnet with a force F. So its mass is m, acceleration due to gravity is then g. So mg is the weight. Mg, this will be the weight of this magnet. And we know here that net force which produces the acceleration in the magnet, here is F dash, this will be equals to mg minus f, mg minus f. So acceleration of the bar magnet, that will be A is equals to net force F by its mass. So this will be equals to mg minus F by m. This equals to mg by m minus F by m. This equals to g minus F by m. Definitely F by m has its value, positive value. So here we will see g minus some positive value, that will be equals to a. That means a is less than g. So acceleration produced in the magnet is less than acceleration due to gravity g. Thank you very much.